Uh, Now we return to the topic of a gravitational position system, GPS. Remember we talked about the fact uh, we need to make relative correction in order to make the GPS to work properly. Uh, we will discuss that in chapter 4 when we talk about curvature, so we imply the gravitational time dilation. The point is that the satellite up in space, high up in space, will have at a different gravitational uh, point compared with the ground, and so there's gravitational time dilation. And also, it's moving with high speed, so there's the uh, relativistic time dilation due to relative motion because therefore the clocks on the ground and on satellite are running at different rates, and we combine their uh, the effects, so get a total uh, change due to special and general relativity. We have the gravitational time effects, and we have the relative motion effect. And here's the how this result emerged from the description of gravitational field as a curved space-time. This was done as an example 6.1 in the book. We talk about curved space-time and the operation GPS. So we need to compare the proper time rates recorded by the clock and satellite, and uh, keep in mind the proper time on either Earth or satellite, but let's talk about Earth first, is directly related to the invariant time interval, uh, ds. So therefore, the proper time is related to ds squared this way. And then from Schwarzschild solution, ds squared is related to 1 minus short radius for r, the time term, and then there's the azimuth angle term, because we're talking about fixed radial and fixed polar angle, because we will cross a plane with fixed theta equal to 90 degrees. Now, the short radius term will be replaced by the expression for gravitational potential, so therefore this is the curved space expression for this proper time. Now, we divide both by c squared t squared term on both sides. Then on the left hand side, I have t tau dt squared, and on the I have this term just copied over, and here also I have minus become r d phi over c dt, so the whole thing squared. Now, r d phi dt, that's a tangential speed. Okay, so therefore this expression can be written, this both a square term, so I take the square root on both sides, so this just the proper time differential property with respect to coordinate time equal to 1, because I take the product from the square root, this is equal to just 1/2. So divide a half, so just get rid of the factor 2, and here you get a factor 2 in the denominator. Okay. So this is expression of the uh, proper time on Earth compared to coordinate time. For example, it's taking the center of the Earth. It's exactly in the same way for the satellite proper time with respect to the coordinate time. Is this just replace the for the Earth ground by the satellite. Then the ratio of these two proper times, then it's just this term. This is in the denominator now, so therefore we'll put on numerator. You have to change the sign. This should be change the sign, and so this become minus and become plus. Okay. But that's exactly the same result we obtained in the previously. Okay. So therefore, it's not surprising, because in the last derivation you may think it's somehow special relativity distinct from general relativity, but special relativity is, of course, is part of general relativity. So the special time dilation must be part of the kinematics for the general relativity. And that's why automatic comes out here. And also because Schwarzschild geometry curves space-time will be involved uh, bending space-time in the time direction. Uh, so you get these factors. Okay, so they come in a nice uniform way, unified way rather. So the takeaways from the lesson 14, we're saying the spherical metric has two scalar functions, g naught naught, grr, and Schwarzschild solution is directly related to the Schwarzschild radius, which is 2gm over c squared, which is a very small quantity. So therefore, GR correction in general is very small in our cosmic neighborhood. And the proper time, proper radius is related uh, to coordinate time, coordinate radius in a curved space in this way because g00 no longer equal to -1, grr no longer equal to 1. So therefore, they differ by this square root factor. And one way to visualize the curved surface is to embed them in a fictitious space. So when you see pictures, people illustrate gravitational time dilation like a bending a trajectory of a particle or light. If they're really talking about embedding space, okay, remember this is fictitious space. The help is to us to visualize. And also we talked about going back to the GPS operations, and it can be obtained very efficiently through the metric description of curved space-time. Next lecture, we discuss further the geodesics in the curved space-time, in the Schwarzschild space-time, and we talk about geoprediction of light deflections, and also talk about gravitational lensing in general. Then we talk about how the orbit of a planet, for example, Mercury, with the whole planet would be precessed due to the GR effects. And that's turned out to be the first instance Einstein realized his theory can be matched by observation. So that's the end of this lecture 14.